Hello everyone, welcome back. In this video, I want to talk a bit about parallel and perpendicular lines, although most of our time is going to be spent talking about perpendicular lines. Let's go ahead and start with a definition of what it means for a line to be parallel or perpendicular. And really we're talking about pairs of lines here. So for our first definition, we say two lines are parallel lines if they have the same slope and different y-intercepts. We're probably pretty familiar with the concepts of parallel and perpendicular lines from geometry. Just really quickly, so let's draw some examples of some parallel lines. So they just have to have the same slope but different y-intercepts. So here's an example of two parallel lines. Our parallel lines could also be horizontal lines or even vertical lines. Right? So here we have three examples, three different sets of lines that are parallel to each other. And one of the important things to remember about parallel lines, which will show up when we start working with systems of linear equations, is parallel lines do not ever intersect each other. So parallel lines, they have the exact same slope, the same rate of change. So if you know the slope of one of the lines, you also know the slope of the other. You just have to use the fact that they have different y-intercepts or go through different sets of points to find the rest of the equation if you know one and want to find the other. So let's go ahead and start our discussion about perpendicular lines with the definition. So we say that two lines are perpendicular to each other if they intersect at a 90-degree angle, which is equivalent to their slopes being negative reciprocals of each other. And so what that means is if one of our pairs of perpendicular lines has a slope of m, then the other line is always going to have a slope that is the negative reciprocal of the first line. So that means its slope will be negative 1 over m. So another way that some textbooks phrase this, although I don't think it's super helpful, is that perpendicular lines are going to have slopes whose product is always equal to negative 1, meaning if you take these two slopes and multiply them together, you always get negative 1. That's, I think, just a convoluted way of saying they're negative reciprocals of each other. So I think this first definition of perpendicular lines dealing with the 90-degree angle at the point of intersection is the one we are most familiar with from geometry. I want to spend a few minutes, though, showing that these actually are equivalent and that one implies the other. And to help us start that little proof or argument, let's go ahead and draw a picture. All right, so here we have a picture drawn of what just two random perpendicular lines might look like. And these aren't perfectly perpendicular because I drew them, but I did the best I could. And so now I want to make an argument, pretty much a geometric argument showing that, well, if our perpendicular lines actually do intersect at this 90-degree angle, then that must mean that their slopes are negative reciprocals of each other. And so the first thing we're going to have to do is kind of get some way to quantify the slopes of our two lines. Let's maybe start with our green line. And the way we can remember, or the way we can think about our slope is like the change in y over the change in x, or the rise over the run. And so I'm going to go ahead and draw this little right triangle to help us visualize the slope here for our first green line. And so we're going to need some side lengths to help us label our little right triangle here. Let's go ahead and use A and B. Well, a couple things to notice are, well, these are side lengths of our triangle. They're both positive. A is like the change in x, and B is like our change in y. So if we want to describe the slope of our first line, our green line, using the change in y over the change in x, that would look like B over A. And so now we want to set up the same kind of picture for our blue line, but we want to use an important observation. And that observation is this relationship between our perpendicular lines. They intersect at this 90-degree angle with each other, which also means we can think of if we were at this point of intersection and took our green line and rotated our green line 90 degrees about our point of intersection, it turns into our orange line, our other line, the perpendicular line. But if we rotate this green line 90 degrees to turn it into the blue line, that means this triangle related to the slope of the green line will also get rotated 90 degrees. And well, if we take that triangle and rotate it 90 degrees. And so if we take that little green triangle and rotate it 90 degrees, it's going to turn into this little orange triangle, right? So the base of our green triangle, when rotated 90 degrees, turns into a vertical line when it was a horizontal line. And the height of our little green right triangle, when rotated 90 degrees, goes from a vertical line segment to a horizontal line segment. So this length that was the height of our green triangle is now going to be the width of our orange triangle. That'll still be B. And now A, which was the width of our original triangle, is now going to become the height of our perpendicular triangle, or triangle corresponding to our perpendicular line. And so now if we want to find the slope of our second line, that is our orange line, which we know is perpendicular to our green line, our first line, we just use our slope formula, the change in y over the change in x. And that looks like A over B initially, but there's one kind of thing we have to throw in here at some point, and that's well, in our original picture and setup, A and B were both these positive numbers, giving us this positive slope, which makes sense since our green line was increasing. It should have a positive slope. But we can clearly see from our orange line, it is decreasing and going down, so it should have a negative slope, and we have to incorporate that into our calculation in some way. There's lots of ways to kind of incorporate that. I think the way I usually like to do it is, well, normally we thought of B as like the change in y, and as we go from left to right on our green line, we're increasing, so that change in y is going to be a positive quantity. And now, as we move along our orange line, our change in y as we go from left to right, we're going down, so maybe this should be negative A or a negative quantity. So we have to kind of allow a negative side length for our triangle, but really that side length is describing a change in y or x and not an actual length itself. But the whole point of this picture is to make this argument that we have in our definition over here. If we compare these slopes of these two lines, they're just flipped over versions, right? This fraction just gets flipped over and multiplied by -1. That means they have to be negative reciprocals of each other. And so we still want to think of this kind of graphical interpretation of two lines are perpendicular if they intersect at a 90-degree angle. But now when we're doing the algebra of like finding the equations of these perpendicular lines, this fact about their slopes is going to be super important and helpful for finding the equations of our perpendicular lines. If we know the slope of one of the lines, then we also know the slope of any perpendicular line. Just take the negative reciprocal of that first slope. In this example, we are asked to find the equation of the line perpendicular to the line described by y equals -3x plus 4. And we're also told that our perpendicular line is going to go through this single point 3, -1. And so to help us find the equation of our perpendicular line, we have to use our definition of what it means for two lines to be perpendicular. And in particular, we need to use the fact that perpendicular lines have slopes that are negative reciprocals of one another. So we know the equation of our original line is going to be -3. We can read that from the slope-intercept form that our original line's equation is in. And now we want to use that to help us find the slope of our perpendicular line. And you'll often see this symbol, this little upside down capital T. It's just a way to denote perpendicular lines because, well, those two lines are meeting at a 90-degree angle in that upside down capital T. So what do we know about the slope of any perpendicular line? If we know the slope of our original line, it's always the negative reciprocal of the other line. So if we think of that original slope, -3, as -3 over 1, first we have to multiply it by -1, which is going to cancel that negative out, then reciprocate it, or flip that fraction over, and so that'll give us 1/3 as the slope for our perpendicular line. So what we know so far about the equation for our perpendicular line is that its slope is going to be positive 1/3. And so the equation for our perpendicular line, if we're writing it in slope-intercept form, which we usually try to do, is going to look like y equals 1/3 x plus b, where b is the y-intercept of that perpendicular line. Unfortunately, the point we were given, 3, -1, is not the y-intercept, so it does not tell us the b value right away, but we can use that to help us find that missing b value, because we know if we plug in y equals -1 along with x equals 3 into the equation for our line, it'll give us a true statement with only one unknown, that unknown being our number b. So if we simplify our equation, we get -1 on the left-hand side, 1/3 of 3 is +1. So now if we subtract 1 from each side, we find that b is equal to -2. So we found the y-intercept for our perpendicular line. It happens at the point 0, -2. So that helps us put this information together along with the slope of our perpendicular line to find the equation of our perpendicular line. And that's y equals 1/3 x minus 2.